Hi, thank you for the introduction. So I'm going to talk about ultra-lightweight superconducting coils for active radiation shielding and energy storage. I'm actually presenting it on behalf of Rainer Mainka. This is a collaboration activity between the US partners in US as well as in Europe. So what are the different ways we can shield from the radiation in deep space? The two possible combinations, one is the passive shielding, which is intrinsic to the mass of the rocket that is there. I mean, typically they are built out of aluminum. So they provide effective shielding, as well as the water they carry on board, as well as the food and the fuel. All of them can act as shielding as well. So this is all part of the passive shielding, which is intrinsic to what is carried on the rocket itself. But by itself, it is not unable to provide the adequate shielding because the amount of mass that is required is really huge, and it would just be cost prohibitive to launch a very heavy spacecraft. So we look at the other combination, which is based on active shielding. By active shielding, what we are trying to achieve is something that happens on Earth, has a magnetic field which protects us from the radiation coming from outer space. That's something that we are trying to recreate on a spacecraft by surrounding it with a magnetic field. So this study has been done as a part of NIAC phase 1, phase 2. Phase 1 is already complete and the phase 2 is underway. And the project title is Magnet Architecture and Active Radiation Shielding Study. I'm not going to talk about the entire project as such. I'm only really going to focus on the concept of expandable coils. The keyword for the entire presentation being expandable. And I will elaborate more on the expandable aspect in the next slides. Okay, before I start, a little bit about the environment in space. The space essentially has radiation coming from different sources. There are these galactic cosmic rays as well as solar particle events. And there's a lot of gamma rays. So the astronauts needs to be protected from all of this. So here are the two spectrums that are shown. One is showing the cross-section of galactic cosmic rays, some of the important elements like the iron, which can do a significant damage if the energy is deposited in the body. On the right, you have is a spectrum which is showing the intensity of protons in the various events that can happen, in both the solar as well as in the galactic cosmic ray. There's a lot of research that's going on to quantify the radiation and the damage that it can cause on the human body. A little background on the active shielding. Active shielding concepts have been developed for many, many years now, and all of them are either typically based on traditional coils like toroids or solenoids. But one thing that is common to most of these coils is the fact that they are all based on rigid structures. So they have to be built on Earth and then somehow being transported to space. And they have a very strong and heavy support structures. The one thing that has been proposed as a part of this NIAC project was to develop expandable coils, or a concept which is based on expandable coils. Expandable coils which are ultra light, which then gives us the flexibility to fold them and then put them on a spacecraft, take them and expand them in the space. So first thing that I need to be proved is the fact that the HTS, the superconductors, can retain the property once you change the shape of the superconductor. I mean, that's not usually how the superconductors have been used. I mean, for various accelerator projects and so on, superconductors have always been rigidly fixed in their positions and you have a lot of support structure. But this one thing that's unique that is being done here is that we are going away from that and we are saying that we can expand, change the shape of the superconductors while they are in operation. And that's been demonstrated by two experiments that were done, one at AML, Advanced Magnet Lab, as well as at NASA. Here we show a small coil which is built out of YBCO superconductor tape, and the two pictures show on the left you see an expanded coil and the other one where you have a folding mechanism whereby while the magnet is charged you can fold the surface. And then we have seen that the current density doesn't change when we fold it, so hence demonstrating that it can be operated in this mode. Similar test was also performed at NASA. And they have also demonstrated that these tapes can operate while the shapes is being changed. So we have demonstrated the concept of expandable coils. Now how can we use these coils to build magnets for shielding? A lot of work was done in this regard and several designs were looked at, and one design that we have converged to is called a 6+1 configuration, whereby we are surrounding the habitat region with 6 solenoids. And a typical configurations or the range of configuration that we are looking for this system, each of these solenoids have about a diameter of 8 meters and they are about 15 to 20 meters long. And we have a nominal field that we are talking about of 1 to 2.5 Tesla there. And to achieve that, we need a current of about 40 to 200 kiloamp. And this leads to a bending power which quantifies how much the particles get deflected in this field of about 8 to 25 Tesla meter. And this has, all these solenoids have a radial pressure because they like to expand in the force that is generated due to these fields. And that force is quantified as 425 atmospheres. We are going to discuss mainly about the 8 Tesla meter case because at this point we have no measure of really what kind of shielding efficiency this design provides. So we start with a baseline which is 8 Tesla meter, which we think should give adequate, but otherwise we can always go higher. So 8 Tesla meter is achieved by using a 8 meter diameter coil and a 1 Tesla field. So this is implemented using a YBCO, or the plan implementation using a YBCO tape, and it's good to review what is currently available in terms of the tape. What is available right now is a 1 centimeter tape, and the current that it can achieve at around 77 Kelvin is about 250 amp or critical current. We plan to operate this solenoidal array in a temperature of around 27 Kelvin in space, or average temperature, and we can see this chart essentially gives a scaling factor. Don't need to go into detail there. But at this point, with the current technology, what can be achieved is around 22 kiloamps. And this is about a factor of 2 for the requirement. So since we anyway plan to build such a system in 15 to 20 years time or even more, we believe that the technology will catch up and we can deliver that kind of current. Here's the graphical which illustrates this concept. So we have 6 solenoids surrounding the habitat region. Here this is a little blow up there. The habitat is right at the center of the structure, and then you have 6 solenoids protecting it. And there is a 1 solenoid which is compensating for any stray magnetic field that's going through the habitat region. And here we are showing in this particular scale of Orion spacecraft there. There are 2 different types of cooling systems that can be envisioned. One is you can provide active cooling for the superconductors, and then we are hoping that we would not need active shielding, and we are planning to show that active cooling is not needed. Here are the couple of views of these solenoids and how they are implemented. So here is a single solenoid which is wound on a fabric, which is basically woven on a fabric, and there is a strong back, and there are radial limiters constraining the movement of this solenoid. And next picture shows in the deflated view how this fabric would then fit on the strong back and then can be packaged to be put on a spacecraft. This plot is essentially showing you the field that we see in the cross section there, which is cutting through the 2 solenoids, and you have the field region, and this is where the habitat is sitting, but we see that there is a significant amount of magnetic field in this region. To compensate for that, we introduce a compensator coil which would cancel out that field, and a pretty good compensation can be done. For instance, without the compensator the field was around 2500 Gauss, and with compensator we can get it down to 20 Gauss, and the pitch of this compensator coil can be modulated to get it down to even 10 or whatever number. What is recommended is around 50 Gauss by NASA. There are a significant amount of forces that are acting on this array, and how to evaluate the force and so on is a bit of a complicated iterative process between a structural engineering and the magnet design aspect. And this flowchart essentially illustrates that. The typical forces that are acting on each of these solenoids are actually they are being compressed while, and which is shown here. There is a huge axial compression which is coming from the ends. And then you have in the azimuthal direction, there is no net force, but there is a little of a twist effect, which is a very minor effect, which is coming from the pitch length of the windings. And then in the radial direction, you have a force which is being exerted outward. So this coil is being compressed and radially expanding at the same time. And these are the dark red line is the where it is in contact with the adjacent solenoids. And there was a lot of work that was done with regards to the structures, or developing the structure for such a system. And because this structure has to be ultra light, and a bird cage kind of structure has been developed for that. And here we have some views to show this. With this kind of structure, we see the maximum deformations that can happen in this array is in the range are shown here. In the extreme scenarios, you have about 0.4 meters of deformations happening on the fabric of these solenoids. But when you translate this in terms of the field, there is no significant impact on the field itself. So what kind of protection can this system give with the 8 Tesla meter bending power there? So here, there are a lot of information presented in this graph, but let's just look at 2 lines without any field, and the dark blue line, and then a dashed blue line, which is essentially showing with the field, comparing these 2 scenarios. And then we can see that there is a significant reduction in terms of the dose that is delivered. But we would like to see even more, and since we are now exploring the possibility of 16 Tesla meter case. So that's all I would like to speak about the array itself, and we can use this concept of expandable coils also to implement a magnetic storage system. And this is just a concept, and we are proposing to for NASA for further funding to investigate. The concept here lies in the fact that we want to develop a cable which has the superconductor which is housed in a flexible cryostat tube. And here is visually what you can see. The picture on the right shows the cross section of such a cable which has a flexible tube, and then the support structure. This is the superconductor layer and the coolant which is flowing inside. And this can be deployed on the surface of a planet, which can be folded, taken up, and deployed in the space or on the surface. So with that, I would like to summarize. The main point I want to make is the concept of expandable coils has been proven, and then this can be applied to either space radiation shielding or can be expanded to include even the energy storage systems. And with regards to 6+1, the radiation protection system, we think it would be better to go to even 16 Tesla meter in terms of radiation efficiency. That's pretty much it. Thank you.